This is Daniel Coosbury, and in this video I'm going to show you a couple of examples of confidence intervals for the population proportion. So just a reminder, this is the formula for how to find a confidence interval for the population proportion. So first, these two central limit theorem conditions need to be met. You got to check that n times p is greater than 10, and n times 1 minus p is also greater than or equal to 10. And if that's true, then the 100 times 1 minus alpha confidence interval is given by this formula here, where the point estimate is p hat and the margin of error is all this stuff. And of course, this is the other way to write it, where this is your lower endpoint and your upper endpoint. So I'm going to use this formula as I walk through a couple of confidence interval examples. So for one, we have a sample of 42 water specimens taken from a construction site. And then 26 contain detectable levels of lead. And we're going to construct a 90% confidence interval for the proportion of water samples that contain a detectable level of lead. So let's start by checking the central limit theorem conditions. So for one, I need to compute my p hat to begin. Well, I'm going to skip this for a second because p hat goes down here. Our point estimate for any confidence interval for the proportion is going to be p hat, which is going to be x over n, which is given by the number in the category over the total sample size, so 26 over 42. And I don't know that off the top of my head. Somebody do that in the calculator. 26 over 42. And I get 0.6. I'll round that up to 0.62. So that's my point estimate. And that gives me the best single value estimate for what p is. Now, of course, I'm going to put a margin of error on that to give you the whole interval. But now that I have that, I'm going to do my central limit theorem condition. So I'm going to check n times p. In this case, it's p hat needs to be greater than 10. And when I need to also check that n times 1 minus p hat is also greater than 10. So if that's the case, n is equal to 42, p hat is equal to 26 over 42. So this is going to work out okay because our sample is going to be big. So this is going to be 26, which is bigger than 10. Now I need to check that n times 1 minus p is also bigger than or equal to 10. So n is equal to 42. 1 minus p is the opposite of this. It's going to be 0.38. And this should work out. This should work out well too. So this is 42 times 0.38. And that's 15.96, which is bigger than 10. So we're okay. So we're good here, we're good here. We already have our point estimate, so we can go on and work on the margin of error. The margin of error is given by this formula, z sub alpha over 2 times the square root of p hat times 1 minus p hat. All of that's over n. And so I've got to plug in things like n and p hat, which I've already found. And I need to find z sub alpha over 2. Let's see if I can make that a little bit bigger. So alpha is equal to, in this case, I'm doing 90% confidence. So alpha is going to be equal to 0.1, which means on my standard normal curve, z sub alpha over 2 is going to be right here. So alpha divided by 2 is 0.05. There's a negative alpha over z sub alpha over 2 over here. This is a little bit too big. Let's try that. And so that means that the area bigger than this number is equal to 0.05. The area less than this number is also equal to 0.05. And it means this middle 90, let me change the color. This middle percent is going to be 90% of the distribution. In other words, if the area under the whole curve is equal to 1, this right tail is equal to 0.05, this left one's equal to 0.05. This is the middle 90%. So that's kind of what we want. So we want the number for which the right sliver above it is 0.05, which means the left part of the stuff below this number is equal to 0.9 plus 0.05, or 0.95. So that's the area to the left that we need to put in to find this critical value. So you can do this in your calculator. Z sub 0.05 is equal to inverse norm, which is area to the left is 0.95, 0 and 1, because we're doing the standard normal. And let me do that real quick. So I'm doing inverse norm 0.95, mu is 0, and standard deviation is 1. And I get 1.645. That's usually written as 3 decimals. 1.645. So then my margin of error becomes 1.645 times the square root of p hat, which is 0.62, times 1 minus p hat, all over n, which is 42. I'm going to do 1.645 times the square root of 0.62 times 1 minus 0.62, and notice how I put a bunch of things in parentheses now, all over 42. That's all under the square root. And I get 0.12. I'll just round it to 2 decimals. I think that's okay. I'll do 0.12 as my margin of error. Great, so now I've got my point estimate is equal to 0.62. I think that's right. Yep. And my margin of error is equal to 0.12. So now I can talk about my confidence interval. My confidence interval is going to be 0.62 plus or minus 0.12. So that's one way to write it. So there's the point estimate, there's the margin of error. This means give or take 0.12. My other way of writing it is where I put this minus that on the left side and this plus that on the right side. So on the left side, I think if you do the subtraction, you get 0.50 even. On the right side, if you do the addition, you get 0.74. So I'm saying virtually this. And this is how I would interpret this. We are 90% confident that the proportion of water samples that contain a detectable level of lead is between 0.5 or 1/2 and 0.74, which is almost 3/4. So you could say roughly, I'm 90% confident that roughly 1/2 to 3/4 of the water samples are going to contain lead, detectable levels of lead, which is pretty bad. It's either half of them or it's 3/4 of them or it's something in between. All that's pretty bad. So that's how you do a confidence interval for the proportion. Let's look at another example. This is going to work exactly the same way because we're dealing with a proportion still. But I want to do it anyway just because it's kind of fun. In a recent poll, 1,143 likely voters, 654 reported that they would vote for a Democratic candidate over a Republican candidate in the next presidential election. Construct a 95% confidence interval for the proportion of likely voters who will vote Democrat in the next presidential election. So we've got a poll and we've got poll results, but what we want to do with any poll is you don't want to just report this number. You want to report the proportion and then the margin of error, because this doesn't mean that out of any group this size you're going to have that many vote Democrat. It just gives you an idea, and you'll use the confidence interval to produce a better estimate, which will be a range of values, not just one value. So we can check our CLT conditions. Actually, first let's do the point estimate because we need p hat. So p hat is equal to x over n, which is equal to 654 over 1,143. And I don't know that off the top of my head. Great, and we get 0.57. Let's do 0.57. So 57% is my p hat. The central limit theorem conditions are, they're not too hard to check because you're doing n times p. In this case, we'll use p hat. This isn't very interesting because n is this and p is this, which means n times p is 654 over 10, which is greater than or equal to 10. So this is fairly easy. N times 1 minus p hat is also going to be really, really big. Do that real quick. We're not going to have a problem. Our sample size is huge, so we're not going to have an issue. And you get 491.49, which is definitely greater than 10. So we're okay, and we're okay. We can go on. So our proportion is 0.57. Let me jot that down up here. Our margin of error is given by the formula E is equal to Z sub alpha over 2 times the square root of p hat times 1 minus p hat all over n. And so I have p hat, I have n, I need to get Z sub alpha over 2, and since I'm doing 95% confidence, that means alpha is equal to 0.05, means alpha over 2 is equal to half of that, which is 0.025, which means that on my normal distribution curve, the number here is 0.025. There's the negative of that number over here. And what that notation means is this little sliver up here is 2.5% of the distribution. This little sliver down here is also 2.5% of the distribution. And it means this middle sliver, this whole white area, which I'm going to shade red, is the middle 95% of the distribution. So if you add all three of those things up, you get 1, which is exactly what we need. So I'm looking for this Z value for which the area to the right is equal to 0.025. So then Z sub 0.025 is equal to the inverse norm. And I got to put in area to the left in here, not the area to the right. So the area to the right is this. The area to the left is the opposite of that. And you get that number, which if you do that to your calculator, you get 1.96. So then E is equal to 1.96 times the square root of 0.57 times 1 minus 0.57 all over n, which is 1143, and that's all under the square root. So I'm going to do all that in my calculator real quick. And you get 0.0287. I'm just going to round that to just to 2 decimals. So I'm going to round that up to 0.03. Just because. So I have p hat is equal to 0.57, and I've got the margin of error is equal to 0.03, which is nice. There's a 3% margin of error, which is nice for a poll, frankly. You could shrink it if you wanted to, take a bigger sample. But what I'm saying is my confidence interval is the point estimate plus or minus the margin of error. So this is usually how polls are reported. Typically, you don't see them written as decimals. Typically, you see poll results like this reported as this is the proportion. The margin of error is plus or minus 3%. So typically, you see it like the red, not like the black. But in this class, we're going to write it like the black. And then you can write it as the left endpoint and right endpoint, which is not usually how you report polling data, but you can do it anyway. And some would argue you should. So this is going to help our interpretation at the bottom. So like I said, when you see polling data reported, or if you're doing it yourself, usually you report it like this. Like this was the answer in the poll, response in the poll, plus or minus 3%, which I got from the black letters. It's just these two things. But the way we could write our interpretation is that we are 95% confident that the proportion of likely voters who will vote Democrat in the next election is between 0.54 and 0.60, which are those two endpoints there. So that's nice. That both of what's nice about this is if you're trying to use this data to decide, like right now, is the Democratic candidate going to get elected in this area or wherever we polled, this confidence interval, both of these endpoints and everything in between is well over 50%, right? You need something bigger than 50%, to get someone elected. And with this kind of poll and the margin of error, you're well on your way to getting elected because you really only need 50% plus one person to get elected. And this says, I'm pretty sure you're going to get at least 54% of the vote, up to maybe 60%. And frankly, 54% of the vote's great. It's enough to get you elected. And frankly, that amounts to millions and millions of people. So all that is to say, this method is used and is often used to interpret polling data and to report polling data. And we can do it because we've got a big sample size and because we know a little thing or two about the central limit theorem and the formulas that are going to allow us to make these things. So that's how you do virtually any single proportion confidence interval.